Good afternoon and welcome to the second lecture of Lesson 2. Last week we talked about series circuits. This week we're going to talk about parallel circuits. So last week was Chapter 4, this week is Chapter 5. But before we go on to Chapter 5, let's review Chapter 4. So what I have here is a series circuit. And as we also know, there are 4 characteristics. The first one listed here is current is constant in all points of a series circuit. So current is constant. And that's because we only have one path for current to flow. So it's going to flow at the same rate through all parts of the circuit. Second, total resistance is the sum of the individual resistance in the circuit. So total resistance is the sum of R1 plus R2 plus R3. That's pretty simple. All right. The total voltage is equal to the sum of the voltage drops in the circuit. Which means since we have one path for current to flow and constant current, but we have different resistances, there's going to be a voltage drop equal to the current times the resistance for each resistor. V3 equals R3 times I. There we go. So total voltage is going to equal to the sum of these voltage drops. And of course power, since we have individual voltage drops, which means we're going to have individual power dissipation at each resistor. So the total power is the sum of the individual power consumption. So while we're sitting here, not doing a whole heck of a lot right now, let's have a look at how we calculate all this. All right, in this circuit, I've got 3 resistors. R1 is 3K, R2 is 7K, R3 is 10K ohms. So if I want to know the total voltage or the total current through this circuit, I just need the total voltage equals the total resistance times current, or current is equal to total voltage over total resistance. So I can see here that I've got 3K and 7K and 10K, which means I have a total resistance of 20K ohms. My total voltage here is 10 volts. So my current is 10 volts over 20K ohms, or 500 microamps. That is 500 1/millionths of an amp, or 0.5 milliamps. You can phrase it or write it either way, it's the same value. So your voltage at R1 equals 3K ohms, the value of R1, times the current in the circuit, or 0.5 milliamps, which equals 1.5 volts. Voltage at R2 equals 7K ohms times 5.5 milliamps, or 3.5 volts. And the voltage at R3, of course, is going to equal 10K ohms, the value at R3, times the current, 0.5 milliamps, which will give you 5 volts. So if you add those up, 1.5 and 3.5 equals 5, plus 5 volts, that equals 10 volts. So we have proven Kirchhoff's voltage law as well as Ohm's law. All right, now what's the power consumption at each point, at each resistor? Well, we already know that current is equal to 0.5 milliamps. And we know power is equal to voltage times current. So I know my voltage, I know my current. So 10 volts times 0.5 milliamps is going to equal 5 milliwatts. Now let's prove that this last portion here. Let's figure out the power consumption at each resistor. So power at R1 equals 0.5 milliamps, or 500 microamps, 0.5 milliamps, times 1.5 volts, which is the voltage drop we calculated at R1. It's going to equal 0.75 milliwatts. At R2, we have 500 milliamps times 3.5 volts, which was the voltage drop at R2 as we calculated up here, which comes out to 1.75 milliwatts. Now remember, a milliwatt is 0.001 watt. So 0.00175 is equal to 1.75 milliwatts. I've noticed in the homework, people are dropping the metric value, which changes the value of this completely. So we don't want to be dropping that, and we've got to know what it means. So milli, 1/1000th. That's what milli stands for. Okay, finally, the power dissipation at R3 is 0.5 milliamps times 5 volts, or 2.5 milliwatts. Add these guys up together, and you're going to find that they equal 5 milliwatts. So the rules mathematically work out. Okay, but what if I don't know all the values? I've got no idea what R1 is up here. Well, we know what it is because I'm taking the same problem. Nor do I know what my total voltage is. So I want to determine the total voltage and the value for R1. Well, I know what my voltage at R1 is, but that's about it. At R2, I know the resistance value and I know its power dissipation, which means I can figure out the voltage drop and the current, or the current and then the voltage drop. So this guy obviously is giving me the most information, so we're going to work off of him. So R2 power consumption provides the information needed to give me the current and the voltage at R2. So the power at R2 is equal to current times the voltage at R2. At the same time, voltage equals current times resistance. So the power, if I substitute the IR for the V back in this equation, I end up with power equaling voltage, IR, times current, I, which gives me I squared R. Or if I drag the equation out, I get current equals the square root of the power at R2 over the resistance at R2, which is going to equal 1.75 milliwatts over 7k ohms. So the current at R2 is equal to 5 milliamps. Now I know what the current is for the whole circuit. 0.5 milliamps. So the voltage drop at R2 equals 3.5 volts. All right, now I can figure out the rest of my values here. Using the current and the value at R1, pardon me, the current and the voltage drop at R1, I know that R is going to equal volts over current. So the voltage drop at R1 is 1.5 volts. The current is 5.5 milliamps. So your value for R1 equals 3 k ohms. So now my resistance total here is going to equal R1, 3 k ohms, plus R2, 7 k ohms, plus R3, 10 k ohms, which equals 20 k ohms. I now have current. I now have total resistance. So my total voltage equals 0.5 milliamps times 20 k ohms, or 10 volts. Take the component you know the most about and work it out. Now, I could ask all kinds of other questions about this circuit. If I have worked out the problem once, say I'm taking or doing an exercise and it has multiple problems on the same circuit, once I've worked this out once, I don't have to work it out again. I can always cut and paste and select the answer I need out of the myriad of answers I've got there. But it gives you all the formulas that you're looking for. So you're showing me your work, and it gives you all the answers you could be looking for. If you have to add another answer somewhere in there, then add the answer. But you only have to do the bulk of the work one time. That's a little hint for working on your homework. Okay. Now we have a series circuit with a ground inserted. And once again, R1 is 3 k ohms. R2 is 7 k ohms. R3 is 10 k ohms. If you measure, well, not if you measure, but these voltage drops are absolute. They don't change. Now, what you might see on a meter depends on this reference here. If, let me get all the scribbles out of the way now. There. Almost there. Now I'm there. Okay. Remember, the ground point tells you where to put the ground or the negative reference on your meter. Now, if it is closer to the plus side, then your measurement's going to come out looking negative because your ground is now sitting at a higher level than your plus lead. So in this case, the voltage from points A to B is going to measure 1.5 volts. But because of this ground point, points B to C, you're going to read a negative 3.5, because that's the voltage drop here, and your negative lead is once again higher than your positive lead, higher reference level. However, if I look at points A to C, no ground point reference there, so my positive probe's going to go there, my negative probe's going to go there, and I'm going to be reading positive again. And then D to B, of course, point B has got a ground shown on it, so you're going to put your negative lead there, you're going to put your positive lead there. This reference is higher than your positive, therefore it's going to read a negative 8.5 volts, because 3.5 and 5 equals 8.5. It's really that simple. All right, now that we've had that quick review, let's start talking a little bit about parallel circuits. All right, we have got the characteristics of parallel and how to figure out resistance in parallel and where conductance finally comes into play. Back in Chapter 2, I was talking about how conductance is going to play an important role later. Well, this is when it's going to play that important role. We'll be talking about power in parallel circuits and how to analyze parallel circuits with random unknowns, and we'll talk about opens and shorts. And of course, we're going to have some demonstration going on in there too. So let's get down to it. Characteristics of a parallel circuit. Well, in a parallel circuit, voltage is constant in all points, or in each branch of the parallel circuit. And current is the sum of the individual current consumption of each branch. The equivalent resistance, well, there's a few ways to calculate equivalent resistance. Notice I'm not saying total resistance, because when we're talking about parallel circuits, we talk about equivalent resistance in that we are going to take a parallel circuit that looks like that, and we're going to reduce it to its equivalent single resistor, as if it's a series. So we talk about equivalent resistance as in if it was the equivalent of a single resistor in series with the power source. So the equivalent resistance is less than the smallest branch resistance. So the smallest resistor in the circuit. And then the term equivalent refers to a single resistance that would draw the same amount of current as all the parallel branches connected. And then, of course, total power is equal to the sum of the total power in each branch circuit. A parallel circuit is formed when two or more components are connected across the same 2 points, just like in your house. Okay, in your house you have wall outlets. One is bigger than the other. And then you have this outlet below it, and maybe across the room you have another outlet below it. All of these are in parallel. That is to say, the plus and the minuses are all connected together, separately of course. We don't want the plus connected to the minus. All of those are connected, and I find it easiest to imagine it in a straight line instead of what I've done here. And let's see here. Alright, here's a parallel circuit. In this case, the power source is in the middle. There's the plus side, there's the minus side, and you see my two resistors are connected both to the same minus point and to the same plus point. Same positive and negative sides. Now I can redraw this very easily. Just like that. It's the same circuit. It's just I've moved this so I just get a left to right reading feel. That is easiest for me to glance at. But this is the same thing. In this case I have two equal branches. They call the separate paths for current branches. And if I had multiple resistors in each branch, then it would be a bank. But these are branches. So that's the same as saying 5 ohms, 5 ohms, and it's the same circuit you saw on the other page. As you see, they're both connected if I measure voltage from there to there, of course, because it's connected all to the same line, it's going to read the same voltage there to there. So the voltage is constant across each branch of this circuit. Now, I have multiple paths for current to flow. I have a current path there, and I have a current path there. So same voltage, different resistors, which means I'm going to have different current flow. And now you'll see why why we say current follows the path of least resistance. So here it's going to be an equal split. Okay, 1.5 volts, a 5 ohm resistor. Let me see if I can't find my calculator again. There we go. 1.5 divided by 5 is going to equal 0.3 amps, or 300 milliamps. So each branch here is going to get 300 milliamps of current flow. And the total current will be 600 milliamps. So this is a simple parallel circuit here. Okay, current in a parallel branch equals the voltage applied across the circuit divided by the resistance. Current equals the voltage applied across the current divided by the resistance of the 2 points where the voltage is applied, just like we demonstrated. So each path for current in parallel is called a branch, as we just mentioned. And there we go. That's a restatement on that. That's a restatement on that. Let's keep moving. Okay, here we have two different branches. This side is 10 ohms. This side is 5 ohms. And we have 10 volts. Well, 10 volts over 10 ohms is going to equal 1 amp. Now the side that has the least resistance, of course, should allow more current. 10 volts over, bless me, 5 ohms, going to equal 2 amps, as we see here. So, half the resistance, twice the current. Because what do we know about current and resistance? They're inversely proportional. So, half the resistance, twice the current. And the total current is going to equal 3 amps. Now, once again, total current is still going to equal total voltage over, so since I know the voltage and I know the total current, I can figure out the equivalent resistance. 10 volts over 3 amps or 3.33 ohms. What did we say about equivalent resistance? It had to be less than the smallest branch, the resistance of the smallest branch, which means it has to be less than 5 ohms. And sure enough, it's this case, it's 3.33 ohms. Okay, when checking current for a parallel circuit, you see we've got two different branches, which is why we have two separate arrows. All right. Leading into and coming out of the branch circuit, you have what we call the trunk current. That is the point where all these current paths merge, so the trunk current will be your total current. Whereas if I was to open this point here and stick my ammeter in it and measure, I would only measure the current for R1. In this case, should be 1 amp. If I measure current here, 10 ohms, 20 volts over 10 ohms, I should get 2 amps. But if I'm measuring current here or here, I should see the total of 3 amps, or the total current. So, trunk current, branch current. The sum of the branches equals the trunk. Okay, and we've pretty well looked at this. The main advantage of using a parallel structure, of course, is you don't have to use quite as much wire. Okay, we talk about the main or the trunk line. Trunk line is also known as the main line. And we already talked about that slide there, so we're going to keep on going. All right. This concept of the individual branch currents equaling the total current, or the mainline current, is known as Kirchhoff's current law. So in series circuits, we worked with Kirchhoff's voltage law, KVL. This is Kirchhoff's current law, KCL. And it doesn't matter how many branches are involved, it always applies. The sum of the branch currents will equal the total or mainline current. And here we have another graphic representing, okay, current in branch 1, current in branch 2, current in branch 3. Going into the branches, you have total current. Coming out of the branches, you have total current. But through each of the branches, you only have the branch current. And as we also mentioned earlier, equivalent resistance equals the total voltage available times or over the current voltage, and that will give you the equivalent resistance. A combination of parallel branches is called a bank. So one single parallel circuit together, that is a bank. And we've already discussed all this good kind of stuff, so let's go on to prove it a little bit. Okay, back in series circuits, I had 4 resistors. I didn't get their values right when I made this slide real quick, so I had to remeasure them, and I've got a 4.2 k ohm resistor, a 3.2 k ohm resistor, a 2k resistor, and a 1.1 k resistor. And here they are. Here's my parallel circuit right here. I don't know if it's recording. They used to record cursors. So this one is labeled 3.9, but it came out to 4.2 when we measured. This one is a 3K, plus or minus 20%. So 3.2K, that's not too bad. This is a precision 2K and a 1K ohm resistor. Right now, their total resistance that I'm reading is 509 ohms. Let me switch this up and go to voltage. And then I want to connect my current meter and everything else. Okay, I'm reading 9.6 milliamps. And for those of you still struggling, that equals 0.0096 amps. My meter is actually here. There's no switch. There's actually a current meter right there. So this 9.6 milliamps is my trunk current. I'm providing it 4.82 volts. So that's not really 5 volts DC, that's 4.82 volts. So let's see if my voltage over my measured current is going to equal is going to equal 510 ohms. So bring that calculator back up, and we said 4.82 volts divided by 0.0096 amps equals 5.0208. Okay, let's measure again. Make sure I disconnect the voltage. Once again, we want to make sure it's isolated from... Oh, I don't want to move that. I just wanted to disconnect the voltage and make sure I'm isolated. So 510. 509. Okay, we're going to hook this back up. Once again, to measure current. I'm going to come right over here. Maybe I've got something going. Nope. 4.83. and 9.6. 4.83 divided by 0.0096 equals, well, that didn't come out right. 4.82. I've also got to remember these are 83. These are not the most expensive precision meters in the world. Divided by 0.0096 equals 503 ohms. Somehow I'm off 7 ohms. But once again, I'm going to write that off as being a problem with my meter. More than it is a problem with my math. Okay. Anyway, still it comes out to about 500 ohms, which is less than my 1.1K. So I'm not too happy with that result. Actual result we saw was in math was 503. So somewhere, and it can be as little as a few microamps here, making the difference over here. Once again, I can't get any lower measurement or any more refined measurement than 0.0096. That might be 0.00955. So let's go down and take a look what it would be like. Um, 4.83 divided by 0.00955, 0.00955, there we go, equals 505. So that brought me up a couple. So once again, talking tolerance on the meters, I'll give that 7 ohms. Delta of 7 ohms, which in the grand scheme of things isn't very much. Alright, so that's my demonstration for... Oh wait, I haven't finished demonstrating yet. Alright, so that is my total current. Now let's look at a single branch current. And to do that, we are going to pull my current meter, currently in the circuit, out of the circuit. We are going to put in a jumper and place my original current meter. And now let's take a look at the second branch current. So to do that, we'll lift a leg and we will install my current meter into the second branch. So now I've installed my current meter in from here to here after opening that wire up. So that's where my current meter is currently installed. And what I'm getting here is 1.6 milliamps. Let me bring the camera back up real quick. Okay. So I'm now reading 1.6 milliamps. And my voltage has dropped a little bit to 0.4 or 4.75 volts. Now let me move a lead out of the way here so it's a little bit easier to read all this and untangle some of the knots I've made. There we go. Now, 486. There. So now I'm basically just checking the current flowing through this branch here. So we said the voltage was 4.85-ish. And this is a 3.2 k ohm resistor. So 4.85 divided by 3200 equals about 1.5 milliamps. What was I reading there? 1.6? I'll take it. So this branch current is 1.6 milliamps. Now I can do this on each one of these branches, and it's going to come within a couple hundred microamps of the calculation every time. Yeah, that was 1.5. 1.51. 1.51 milliamps. Okay. All right, now if we just go ahead and work through the math on the rest of them real fast. $4.85 divided by 4,200 equals 1.15. The one I've got marked at 1.9K is actually 2K on the money, according at least it was today. So .0 or 2.4 milliamps. And the 1.1K equals 4.4 milliamps. All right. Do our math. 1.15 plus 1.6, 1.75. .00175, that was that one, plus 2.4, 0024, plus 0.0044 equals .00855 or 8.55, closer to 9 milliamps. Add these numbers up. That was 4.2. This 3.2. That was 2.0. That was still 1.1. Oh, what am I doing? Came out 510. .85 divided by 510 ohms, which was our equivalent. So 0088 instead of .00585. I'll take it. When we start talking microamps, I'm not going to argue too terribly much. If you get it down to 1 or 200 microamps, I'll be happy. All right, so we're going to move on from here. All right, the equivalent resistance, one more time, has got to be smaller than the resistance, or the smallest branch resistance. So in our case, our smallest branch was 1.1K. And our equivalent came out to 510 ohms, thereabout. Now, as you add branches, you're adding more current consumption to the circuit. So as current consumption goes up, okay, each of these branches has its own current consumption. And that current consumption is equal to V over R for each branch. So now I add another branch. My voltage stays the same because I've added another branch. my current is going to go up, what's going to happen to resistance? The total resistance, or the equivalent resistance, since current and resistance are inversely proportional, as my current goes up, then my total resistance has got to go down. Unless, of course, we change the voltage, which we don't do in a parallel circuit. We leave the voltage the same. Every parallel circuit in the world is also known as a current divider, because just like we get different voltages to branch off in a series circuit, we have the availability of different levels of current from a parallel circuit. So parallel circuit current divider, as you add branches, as you add more resistance to the parallel circuit by means of adding branches, the equivalent resistance has got to go down. Okay, here's a case. A single branch, you've got 2 amps. 60 volt source, 1 branch, 2 amps. Same 60 volt source, now 2 branches with 30 ohms. Each of these branches has got to have 2 amps. So the source is sourcing 4 amps worth of current. Same 60 volt source, now we add a 3rd branch at 30 ohms. Once again, each branch is going to take 2 amps. So now we're sourcing 6 amps of current. So as we have to source more current with the same voltage, my R equivalent has got to be dropping off. Now, in a circuit that has multiple branches with the same resistance, we're able to say the equivalent resistance of this entire circuit equals the value of one resistor divided by the number of resistors, the number of branches. So in this case, 1 branch, 30 ohms, it's a 30 ohm resistor. In this case, 2 branches of 30 ohms, 30 divided by 2, this is a 15 amp, or 15 ohm equivalent circuit. And if you want to be sure, 4 times 15 equals 60 volts. In this case, we have 3 branches, equivalent resistance of 10 ohms. Okay? 6 amps of source current times 10 ohms equals 60 volts. So, circuits with multiple branches of the same value, you find out what the equivalent resistance is by the value of one resistor divided by the number of branches you have. But this is kind of a special case. It's not often that you're going to get parallel circuits with identical resistance. The normal way to calculate resistance in a parallel circuit is the current and reciprocal resistance formulas. Okay? The current formula, of course, you get the sum of the total branch currents, or your branch current is going to be equal to your total voltage over your equivalent resistance, or so that's one way to get the resistance in parallel. The other way to get the equivalent resistance, only knowing what the resistors are, is you have 1 over the reciprocal. So 1 over the reciprocal of each resistor. And the sum of the reciprocals, so 1 over the sum of the reciprocals for each branch. The reciprocal, 1 over R, should strike you being familiar, because conductance is equal to 1 over R. So this is another way of saying 1 over total conductance, or the sum of the individual conductance, is equal to the resistance. And don't ask me what just happened there. No matter what happens, no matter how many branches you have or what their values are, this method will always work. So here's a case of R1 equals 20 ohms, R2 equals 10 ohms, R3 equals 10 ohms. Well, the sum of the reciprocal method, 1 over R1, 1 over R2, 1 over R3, or saying 1 over G1 plus G2 plus G3, because of course G is our symbol for conductance. So looking at this one, let's bring up the calculator again real quick here. (20) 1 over x plus 10 1 over x plus 10 1 over x equals 0.25. Take the reciprocal one more time, 1 over x. Oh, and there we go. The equivalent resistance equals 4 ohms. We could have calculated the total current here, where 20 volts divided by 20 ohms, so 1 ohm. 10 volts, 20 volts divided by 10 ohms, there's 2 amps, 2 amps. So total current of 5 amps, 20 volts divided by 5 amps equals 4 ohms, which we have there. This way, I'm getting to it much quicker and much more directly using the reciprocal method or the total conductance method. Here's one of our special cases where all the resistors are the same. So the value of a resistor over the number of resistors you have, so 60 k ohms divided by 3 resistors equals an R equivalent of 20 k ohms. That's pretty easy. Another special case where you only have 2 resistors. And this one has got a acronym, and what you do is you take the product of the 2 resistors divided by the sum of the 2 resistors, or multiply, add, and divide, or the MAD method. Okay, this only works when you have 2 resistors. So R1 times R2 in this case, 40 times 60 equals 2400, times the sum, 100, 2400 over 100, the equivalent is 24 ohms, which they say right there. Now, do you have to remember this? Absolutely not, because you can always do conductance method. So once again, grab the calculator out and 40 1 over x plus 60 1 over x equals, invert it one more time, 24 ohms. Okay, I don't have to remember this at all if I know this one. Okay, once again, let's take the circuit we built ourselves, or the one I built. And let's hit clear. And once again, we're going to take our actual 4.2K, 3.2K, 2K, and 1.1K. Because I measured those values before I started, may as well keep using them. So, go for the clear. 4200 1 over x plus 3200 1 over x plus 2000 1 over x plus 1100 1 over x equals 0.00195 whatever. Take the reciprocal and I end up with 510 ohms. Which, one more time, disconnect that guy. Take that guy down there, isolate the circuit. Well, now I'm bouncing between 507 and 513. So depending on where I'm grabbing and how bad my connection is, I'm measuring about, oops, can't even see that, can you? I'm measuring close enough to 510 ohms. So I'm pretty happy with this, with my results here. Okay, in the 2 resistor scheme, you can, whoops, what did I do there? I somehow changed the size of my board. So let's resize the size of my board. There we go. Alright, you can find for an unknown in the 2 resistor scheme by taking R times the equivalent resistance over R minus the equivalent resistance, and that'll get you there. Now, it is the same thing as taking G total minus G1 minus etc. And you can find the resistance easier, the missing resistor easier using the reciprocal or the conductance method. Speaking of conductance, conductance is equal to 1 over R. Total equivalent conductance of a parallel circuit is given by total conductance is equal to the sum of each conductance. And you already know how to find conductance. It's 1 over R. And we pretty well worked this one to death. So we'll keep going here. Okay, total power. Once again, total power is equal to the power consumption in each branch, the sum of the power consumption in each branch. So the total power is equal to the total voltage times the total current. So 2 ways you can figure this out. Actually, there's a lot more ways than that, because we also have all the other power. Total power is equal to the equivalent resistance times total current squared. We know that also. So many different ways to find power consumption. Alright, here we go. In each branch here, first branch I have 1 amp, second branch I have 2 amps. Total voltage is 10 volts. So 1 amp times 10 volts is 10 watts. This branch is going to draw 10 watts of power. This branch, 2 amps times 10 volts, is going to draw 20 watts of power. The total power consumption of these two branches is going to equal 30 watts. So your power supply has got to be able to support a 30-watt drain. If you've worked on computers, ever had to replace a power supply, you've noticed there's power supplies run different watt levels. Some are 250 watt power supplies. Some of the ones I use in the trainer or in the flight simulator are 80 watt power supplies. Pardon me, 800 watt power supplies. So power supplies will come in different wattage ranges too. Okay, random unknowns. You don't know what one of the branches are. You can find by either the current consumption, depending on if you know what the current is. Well, let's see here. Depending on where the opens and shorts are. In this case, light bulbs, you get an open in the main trunk, nobody's going to light up. In this case, you get an open somewhere in a branch, that branch isn't going to work, but all the other branches will. So this is sort of like the circuit breaker at your house pops and none of the lights on that line come on. In this case, this is more like the light bulb in your bedroom won't come on, but the ones in the rest of the rooms in the house do. So that is an idea of an open. Now what happens when you get an open? You actually lose a resistance. Well, if you get more current draw on the power supply, or more current every time you add a resistor, if you take one away, your current is going to drop. Your current consumption is going to drop. So with that in mind, let me resync here. I'm going to put all my resistors back together. I'm going to look at my total current. Yes, that one goes there. I'm going to go back to look at voltage. Yep. There we go. All right, let's see here. Voltage, I've got. Current, I've got. Turn on the power. Route things around so we can actually see the meter readings. So with all the resistors in place, I can see that I've got 9.5, 9.4 milliamps. I'm still sitting about 4.7 volts. I'll tell you my there we go. Yeah, that's just connection on my voltage regulator. It's not a big deal. Okay, so 9.7, 9.8 milliamps. This side, milliamps. Now what we're going to do is we're going to pull a resistor out of the circuit. And I'm going to pull the 1K ohm resistor out. So I pull that resistor out just like that. So I pull a branch out. That branch is no longer using current, and you can see that my current consumption has dropped. My voltage has stayed the same. Voltage is the same, less resistance, less current. Or pardon me. Because I pulled it out, I now have more resistance. So I was at 510 ohms resistance before. I'm now at 1K ohm? No. Yeah, I'm now up to 1K ohm of resistance. Let's drop that down 2 more. 944 ohms to be exact. Now I'll go ahead and add that resistor back into the circuit. So adding the 1K back into the circuit immediately drops me down to about 512 ohms. And as soon as I turn the circuit back on, my current goes back up again. So that's the sign of an open. When all of a sudden your resistance goes up, your current goes down, and it's not the same as it should be. You got yourself an open. Now a short is a much more evil critter, because a short across, let me come back to this one. A short in a parallel circuit, you see, you're only going across one resistor. However, what you're doing is you're shorting across the whole power supply. You're creating the least possible, least resistance path across your power supply. All the current is going to go through that. So all of a sudden your current skyrockets or cuts out completely because your power supply limits out. And you can no longer measure resistance. All your resistance goes to zero because a short will short out all the branches. It's just like throwing a piece of wire straight across all the branches. So all the current goes across that short circuit. So your current shoots up, way up before it cuts out altogether. Wires start getting hot. Things start smoking up. But let's see here. Random unknowns. Well, let's go back to our circuit, the one I created for you. Here we go. Say, random unknowns, what I do with my pen. I suddenly am unable to find my talking pen. Stand by. Alright, I found my pen again. Okay, say we don't know what that resistance is. But we do know what our total resistance should be. Well, it's easy to figure out because R3 is going to equal 1 over G total minus G1 minus G2 minus G3, oh, forgot about R0, sorry, minus G0. Or we can also say G3 is equal to G total minus G0 minus G1 minus G2. So in this case, I don't know what this 1.1K is, but I do know my total is 510. So I take the total conductance, which is 510 ohms, take the reciprocal, minus R0, or we're going to take G0 at this point, 4200, 1 over, minus G1, 3200, reciprocal, minus R3, or G3, G2, this one. 2000, 1 over, equals 9.10 whatever to the minus fourth. We're going to take the reciprocal of that because R3 equals 1 over G3. Take the reciprocal of that, and I get 1.98.672821, and so on and so forth, which is pretty darn close to 1.1 k ohms. Now remember, this was 510 point whatever. When you start stringing out the decimal points, that's when you get the highest accuracy. When we start rounding up, we start killing the accuracy some, which is why we get something slightly different than 1100. But we get pretty darn close to 1100 ohms or 1.1 k ohms. So for a single missing resistance, subtracting your subconductance, your branch conductance from your total conductance is the easiest way to get your unknown resistor. If you don't know the current but you know the total power, you can work your way through each resistor till you find the values for the missing resistor. All right. If they're asking for power, well, total power is equal to the total branch power. Voltage, if you know one branch current and you know the value of the resistor, you know what the total voltage is, because all the branches get the same voltage. So it's just a matter of remembering the four characteristics. Voltage is the same across all branches. Total current is the sum of the individual branch currents. Equivalent resistance is going to be less than your smallest branch, and total power is equal to the sum of your branch power consumption. From there, it's just a matter of working through the formulas for each branch. And we'll review this more next lecture, don't worry, because the next lecture we're going to be mixing parallel and series circuits together and working our way through them, being able to recognize a series parallel, which is multiple parallel circuits in series, or parallel series, where you have parallel branches made up of series circuits. So we'll get to play all kinds with that. But this is about all I have for this week, unless somebody decides to come ask me questions. Don't forget, Wednesday night, I'm in class, 7 to 9 p.m. Central Standard Time. If you're not stationed CONUS and you need extra help, get hold of me. We will work out a way that I'm able to be awake and work with you when you need to be worked with. Don't let not being CONUS stop you. As long as you got an internet connection, we'll be able to work. And that's about it. So you guys have a good night, and I will talk to you live on Wednesday, hopefully. Bye.